Visible, huh?
Yes.
Yes. Welcome everybody. Good afternoon. And this is SMCB seminar series that has been going on for a while. And to start today's proceedings, I request Professor Ranjit Biswas from SN Bose National Center for Basic Sciences to initiate the process. Yeah, Ranjit, please.
Many thanks, Shumon. It's a pleasure that we are here again on SMCB, which is essentially actually brainchild of Professor Bagchi, focusing on the young researchers. Professor Biman Bagchi is SERB-DST National Science Chair Professor. Today we'll be speaking on, as you can see on your laptop or computer, Stokes law at molecular length scales. Professor Bagchi is the leader in India to make statistical mechanics popular and has made outstanding contributions in the area of ion conductivity, nucleation and phase transition, protein folding, and developing molecular length scale understanding of biologically active molecules such as insulin. His insulin work has indeed been very famous, and many of us being motivated by that work. He has already published 2 books, one on water and another on equilibrium statistical mechanics. The 3rd book on time-dependent statistical mechanics.
No, 4th book. You missed my molecular relaxation in liquids.
That is water, right?
No, molecular relaxation.
Yes, that I have. Yeah. Sorry. And apart from this, he has published 2 other books. One for students focusing on how to be successful in academia. And another book is on his local observations in Malleshwaram. With this, and also Professor Bagchi writes blogs, various interesting stories with profound, intricate connections to our maturity, upcoming, and philosophy. With this, I request Professor Bagchi to deliver today's talk on dynamical linear response of liquid Stokes law at molecular length scales. Professor Bagchi, please.
Thank you, Ranjit and Sumon, and also Rajiv for organizing this for now more than 2 years, because we started this during the pandemic, and in 2021, I think it started, early 2021, called February or so. So it is going on for quite some time now. And I was talking today with Sumon in the morning that, because I'll take 1 minute to discuss this, that there should be certain regularity. No organization survives, in a way without sufficient amount of regularity. And then that, of course, brings the issue: what do we mean by regular? Like TCS once in 2 years, but that I think becomes kind of, to me at least, it loses a little bit of appeal because of the deep separation. 2 years, 3 years, sometimes it's just too much. Since we are doing now founded, and we are going to be active in other much bigger, the Society for Physical Chemistry, that thing has to be kept in mind, that we need to be certain regular. Remember, and I was again telling someone that I was part of several organizations when I was very young, and means first year BSc, MSc, those days, those 3 years, and then we had a science club called Vigyanti, and we used to meet every Sunday, and that was very important. And then I was also a part of a club there called Samoshidi Patel. They are also, of course, 4-5 times a week. But the science club that we had, that once a week was very important. So that is one extreme. We cannot meet once a week. We might be able to meet once in a month or something like that. And in the context of SOPHIC, which the Society of Physical Chemistry that we discuss more, that also would need to bring in certain activities so that it can serve its purpose of bringing people together, scientists together. That's one thing that the Gordon conference, they do so many Gordon conferences, it's such regularity. Yes, there is a liquids once in 2 years, but then water in between. that is every other, and everyone who goes to water goes to liquids almost. And then several others are there, spectroscopy. So people are in contact, and SES in between, two SES every year. And so the kind of activity that goes on, even in Europe, they have a meeting in summer every week. I went to do back-to-back conference in Spain and France. It's amazing that amount of you get information you get and the kind of kick you get out of that. So this is something to keep in mind. I know everybody is very busy and everybody is, but if one can make some time, and you don't have to talk every time very big things, but you talk about your work and you've got a graph, or you got see these results you are thinking. What I'll be talking today is something like that. We submit a paper, and but that's about it. Though we are working on it for quite some time. So something that now coming to the work, something that always kind of intrigued me. It was that the Stokes law, from which Stokes, Einstein and Langevin equation are derived, and people don't know that too well. That everything started at Stokes law. So the first linear response equation in dynamics was written down by Stokes. And that's the relation between force and friction. That defined friction in a kind of a systematic molecular way. It's very, very interesting. When you look at Navier-Stokes hydrodynamic equations, there is no friction there, right? There is the viscosity. So you have the conservation laws, and you have Navier-Stokes equation, where you write the equation of motion for the momentum density and current density, and you have on the right hand side gradient of pressure, and you have the viscosity term in the derivative of velocities. And that viscosity term gives the distribution. That is again from symmetry argument, very, 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 very fundamental. And then, of course, that introduces the definition of viscosity, which then subsequently was done molecular. One need to appreciate there are a lot of very beautiful things, beautiful time-dependent statistical mechanics that go into tying them together in a systematic fashion. And so when I was writing this book, Non-Equilibrium Statistical Mechanics, as Ranjit was saying, this is the fourth book that we wrote. Actually, the first book is the Molecular Relation Liquids, has somewhat in common with this book. So it's a much bigger book and it's a systematic book. The whole idea was to make this subject systematic. I found one thing, though there are great books like Zwanzig and Campaign and book by physicists, it has not been systematic. So people, particular days of molecular dynamic simulations and other things, even more advanced things, not very kind of hodgepodge, unlike in equilibrium statistical mechanics. Take quantum mechanics, for example. Similarly, time-dependent stat mech also is not very well presented. The amount of work has been done, but one has not been able to piece them together in a consistent fashion. So that was the idea of this book. And in the process of doing that book, I started noticing things like, as I said, that in one of the earlier occasions, that the Boltzmann H function and Boltzmann H theorem, which is so fundamental to our understanding of relaxation phenomena, then time constant, then entropy, arrow of time, everything comes from 1872 paper of Ludwig Boltzmann. That's a wonderful paper, actually. There are very few papers of that magnificence have been ever presented. So we went on, and but I found that going to many books, there is not a good calculation of H function. Then I found that 1970s of Kashan didn't have that. 1987 had, but that was a cartoon, and probably was wrong. So we did the H function, HT, and that is in the book. Very, very beautiful result one can get, and more than result understanding. That is a 150 years old function. Earliest time-dependent function. Next, when we are trying to everywhere we did little calculations like that, and we are doing the came to linear response. Then I was thinking, okay, equilibrium linear response we understand. Specificity, isothermal compressibility. These are all equilibrium specific. We know what is the definition of specific heat. Heat by heat absorbed by a given at a temperature, delta Q by T. So we know compressibility, del V by del V. And of course, you are more familiar with the differential form of that. Now, we know that, and then we know there is statistical mechanical exact definition for specificity in terms of energy or enthalpy fluctuation, and you know specific isothermal compressibility in terms of volume fluctuation, you know dielectric constant in terms of moment fluctuation. Dynamics also there are similar things like that, but it has not been that clearly put in. So when you're trying to understand this linear response, that the response that this system gives to the linear order, that I'll little bit discuss, that is very beautiful and also connected with experiment. Then I started looking into that. Then I looked into Stokes law. And now all of us who do physical chemistry or chemical physics or in biophysical chemistry, we know these reactions, okay? Systems are reaction. Then malachite green, crystal violet, all these things, fluorescence properties are intimately connected to certain isomerization. And these are not taught. This should be taught at the level of BSc. FINA, for example, should have this. But these reactions are very fast. And so lasers, when came 1970s and 80s, first thing they did, they took a fast laser, they studied one more fast reaction. And what they studied? They studied the viscosity dependence. How they studied the viscosity dependence? By varying either temperature of the solvent. I'm telling that this diagram was isoviscous plots. So it found that all these reactions have a very strong viscosity dependence, which is shown on the right side, that viscosity 1 over eta kind of it, 1 over inverse viscosity dependence. Then comes another beautiful, and many like that. This is a noble gas. This particular one is, I think, krypton or xenon against viscosity diffusion. But now it is not 1 over eta, as Stokes Einstein says. They fitted it to something like 2 by tau. 1 over eta to the power 2 by tau. Of course, once they pointed out that it's not the right way to interpret it. It's still 1 over eta, but p-factor depends on eta indirectly. Here, I changed the viscosity by changing the solvent. That was the issue that once it made. Then continuous investigations of viscosity dependence of diffusion in the supercooled liquid, the famous decoupling phenomena, Johari-Goldstein mode, translation rotation decoupling, the alpha beta bifurcation. So all is a diffusion viscosity relationship. Biological processes include protein folding, protein-DNA interaction, also one studies viscosity. Protein folding, there are many papers actually in best journals studying viscosity dependence of protein folding, protein-DNA interaction. Today I was doing some Google and I found a nanoparticle rotation in synovial fluid, which is the fluid between our in knee. This I think this these days I'm having pain in the knee, and this usually this fluid becoming gel or not there, and then you do some nanoparticle which goes in there and fixes things. And what they do, they study this nanoparticle, rotational cancellation, diffusion, and viscosity dependence. You just give this title in a Google: viscosity dependence of rotational diffusion, mechanism of chemical and biological reaction. The list is endless. I just gave. So what I want to tell or emphasize that we using the diffusion viscosity relationship again and again. And what gives us this relationship? That is the friction. We always go through friction. If we don't have the friction, we don't have the connection between diffusion and okay. This might look elementary, but to me it is quite fundamental. So we always work with the Langevin equation or Fokker-Planck equation, and the basic quantity here is the friction. But the problem is that friction is not well defined. But anyway, it's a linear response function, and I'll talk about it and the diffusion. Now, friction definition came with Stokes law. These people don't seem to appreciate that, British scientist who wrote with this beautiful thing. He found that if you pull reasonably large particles, like a Brownian motion kind of stuff. Then you get colloid kind of thing that you get the velocity, steady state velocity, which I call V drift, is proportional to the external and 1 over friction. This is the linear response. Remember, specific heat is exactly the same thing. The delta T, you on the left hand side, then 1 over specific heat and the heat given. So this is a dynamical analog of the equilibrium response function, and this is a dynamical response function. And I must point out, this is the first time a linear response entered time-dependent statistical mechanics. Then, of course, in this great paper in 1905, Einstein derived two things. One important thing to know here, the diffusion have an independent interpretation in terms of the random walk. It doesn't need friction. However, in the colloids kind of system, Brownian particle Einstein considered, then friction is related to viscosity, and two together. This is called the diffusion relation of diffusion to viscosity is called Stokes Einstein relation, which is the one which is used in all these examples that I talked. This is the basic thing, but it started with Stokes. So if you want to study, you can. So you have two places you can go wrong. You can go wrong at the level of Stokes law. It's a law. I called it relation, but I should have called it law. The rest of the cases I have called it law. It's a law. It's not relation. Stokes Einstein is relation. Einstein is relation. Okay. Einstein can also be called equation. So how do I think about it? The linear response, the lead and all the formalism by Diego Cubo in 1957. So linear response, as the term linear means, is essentially a first order perturbation theory. In theory, that it comes from a first order that I'll describe in a minute. So in quantum mechanics, we are so familiar with first order, and so we have a perturbation H prime, and then we can describe the wave function, perturbed energy. That's the fourth line. First is the H naught. I've taken the conventional V, and then we decompose the energy of nth level by the unperturbed plus first order, second order wave function similarly. Beauty is that, and this is very, very important for today's talk of any course on time-dependent statistical mechanics, that the correction, energy, first order energy correction is given by the zeroth order wave function. That all of you know, but still should be emphasized. And then wave function is similarly, except there is some and there are some other issues that come. Okay. But it is the first order perturbation, first order modification, first order correction does not need the, I can get away by doing the zeroth order properties. Okay. Now time-dependent quantum mechanics. Again, the same thing happens. It's beautiful. The relationship between these slides I've taken from my book. The theoretical expression of experimental measurements is Fermi-Golden rule, and that is first order perturbation, and with the Dirac solution. And then all the experimental expression of the experiments that we use in theory to explain experiment, like Raman line with IR shape, relaxation, we mostly use Fermi-Golden rule, to the extent that many people have tried to extend the Fermi-Golden rule, saying that it doesn't work. And yes, just like first order perturbation theory lands in a degenerate case, here also degeneracy has the problem. But by and large, it works beautifully. Nowadays, there are a lot of modifications of Fermi-Golden rule. People trying to keep the Fermi-Golden rule with certain modifications, and they are arbitrary, but seems to be working. So, basic idea then, all these starting from this first order perturbation theory, we can go a long way. Why we go a long way? Because what we are getting in first order perturbation, this is what is called linear response. The correction, so the response is the first order. That's why it is linear response, called linear response. Why the linear response is so valid? That is what is still is, should be. I'll show some, but still is very much an interesting and exciting question. And because particularly fluctuations from non-equilibrium state, what can you describe it? There are some beautiful ideas, but calculations are still not too many. Okay. Now, what happened now from time-dependent quantum mechanics to time-dependent statistical mechanics? In time-dependent quantum mechanics, we have the energy levels, they define, and wave functions, they define the phase space. But in classical statistical mechanics, we have phase space, which is by position and momentum. However, when what a Stokes experiment, I pull a particle, that particle, now not colloid, of the size of the same in the solvent, one of the solvent particles, then that is going to alter phase space dynamics. The phase space dynamics, total phase space dynamics is given by Liouville equation. Liouville equation is one part which is in the absence of the external force. There is a modification. That modification is the perturbation, and that perturbation is dealt in a first order perturbation theory. That's what Foucault did. So linear response theory allows you to obtain the effect to first order. So this is the experimental setup, implementing Stokes experiment, and we are having a tag particle, which you are putting in a liquid. They are just to make bigger, so that to emphasize the point, but we have done until you worked on this, and so many different sizes we have done. So now what are you doing? We are doing an extra energy. We are dumping in because we are taking the same size of the solvent much of the time, and when you are taking different size, we modify the interaction potential. So one part of liquid is well defined. So in the presence of the cooling, there's an extra energy. That energy is going to get dissipated through friction, and that is the force dot displacement. So that is the potential. Now again, go back. I write the Hamiltonian, and it's not a perturbation, H1T. And then I have, what is the perturbation? That is the force times this displacement. That is H prime equal to minus Fx for Q1 Ft, cooling in the Z direction. Now, total Liouville operator is a linear. And so in Hamiltonian, it goes over, sorry, it's a linear operator. So it goes over I L naught plus I L1. L1 is the notation problem. H1, H prime, H prime should be H1, it is L1. So Liouville, L naught is the unperturbed phase space dynamics by Liouville equation, and Liouville operator. L1 is the perturbation. So now I'm writing down the Liouville equation. The Liouville equation is the following equation, which is fairly well known, but main thing is that you are thinking just like density in the liquid state. Here you have a density in the phase space, and F is a density function, and that density function is moving because of thermal motion and following Newton's law of motion. And so that is here in terms of Hamilton, we popularly and conveniently used in Hamilton's equation. But we have an equation of motion. Consider Newton's equation. The system is moving in the phase space. And so these are the equation of motion. First one is the Poisson bracket, and that is can now be written in terms of force acting on the particle and the momentum. These are very famous equations, and very in a mutilated form, approximate form, it finds in many Fokker-like equation, Bindike equation, many equations we use this. Okay. The additional term in the basis of now, let us see. So this is something which is you do all the time these days in molecular dynamics simulation. The additional term is really has a, in this particular case, has a very interesting structure. It's amazing. This was actually made me when the day I realized this my day. So I do now is the Poisson bracket, but important thing is that L1 is Fx. Then because if I go the Liouville operator, then there's only one term that is the second term that survives, and that is the force, external force, and the dp1. And this L1, that's very important because L1 has the form, this form. Okay, because it depends on H prime. So I take the derivative with respect to Q1. So in that case, derivative with respect to Q1 only survive, and dH dp1 will give me dp1. So finally, because after L1 there should be H here. That's forgotten. But I didn't do that. But after doing all these things, you get if external, that's time independent, then 1 over kVt, that's Boltzmann factor, and P1. So the L1 F naught gives you a beautiful simple equation. Everything is constant except you have the momentum of the first attack part. So now this structure allows you to do a lot of things. For example, as I said, I could derive Stokes law by using that. That was really nice. So basic scheme is the following: linear equation, perturbation in Hamiltonian, then perturbation in their equation, then you calculate the first order correction. It's all given in my book, and also Kubo and also Hansen method. Then you linearize, right? Go back, put F naught plus del F into full Liouville equation, and then linearize it with respect to delta F and L1, and you find the response. And that leads to time correlation function. This is what in one line, 50% of time difference statistical mechanics in formal level, or 60 maybe. So we start with the Liouville equation, and then we do this separation. F naught is the equilibrium one, del F is the perturbation. That means this is how phase space density gets perturbed. Then we substitute back in the Liouville equation and we linearize. And linearize, then remember df naught d dot I L naught F are equal to each other by Liouville equation. They cancel each other. L1 and delta is the second order. So I have L naught delta F first order and L1 F. So 2. And this can now be solved formally. And again and again, I'm saying that we have a beautiful thing in terms of this. We now know L1 in a very simple way. It's F becomes the X P1. Okay. You don't need to really fully say that, follow all these things, but that then my perturb, just like quantum mechanics, perturb equation of motion for the perturb phase space density is this quantity. Look at the beauty of the right hand side. Rarely you get such kind of a thing, then you can solve it. But what is beauty is that now by using this is a little non-trivial steps, because 2-3 steps in the central step because 2-3 steps of hermeticity and all of things. But you get a beautiful now because of the phase space integration. Because now what I'm calculating here, the response, which is the drift velocity. Because why it is drifting? Because phase space density has changed, delta A. So V1 now is the integration of whole file. D gamma is the integration of phase space. And V1 is my observable, which in Kubo's notation B. So it's exactly I wrote down. So B is this, and delta F is the distortion of the phase space density, and the integration over the whole phase space, dqn, dpn. And once I do that, and I manipulate, I get back this beautiful expression, which is the time correlation function of the time correlation function. I take the long time limit, a steady state limit, B, and behold, you get the diffusion constant. This one on the right hand side, green correlation. But now I have a drift velocity d by kVt as external. I know Einstein, d equal to kVt by zeta. So I derive exactly 1 over zeta fx. This is a beautiful derivation that I've given in my Stokes law from linear response theory. Because I was convinced that Stokes law is the first linear response relation. Then I had to derive it from Kubo, linear response theory. And here is the derivation in full glory. Okay. What are the issues and questions? We have 2 definitions of friction, Stokes law and one from Einstein. Dependent on Stokes law is the elementary, is a law, but Einstein used it. But I told you diffusion does not depend on it is random walk. So there is a transition probability that again ties back to friction. So latter is derived from Einstein formula, the Einstein relation from diffusion and equal displacement. The latter leads to an expression in terms of C that we just showed. Stokes law is still a law. It is written down. And it defines friction. That is where everything started. I now gave you a derivation from linear response theory, which makes at least me personally mighty pleased. Stokes law refers to set up a flow, while Einstein relation is a equilibrium. It is very interesting. Stokes law is macroscopic, but Einstein relation or random walk or velocity correlation function are microscopic. The validity, history of validity of Stokes Einstein has been controversial. There are every year 10-20 papers on the breakdown of Stokes law. I was talking to one of my colleagues. He counted. He said yes, it's about 10 every year. 10 breakdown of Stokes-Einstein relation. Now, I want to now check what do I do. One through derivation by the Einstein derivation of Einstein from Stokes. The derivation of Stokes from Einstein. Sorry. The point is neither not sufficient, neither often not sufficient. This uses various Stokes hydrodynamics, like friction and viscosity. That also called Stokes. So one is Stokes law, another is Stokes relation. This Stokes relation and its proportional viscosity. Diffusion is a very different property. Again, I'll be repeating that random also. But direction is not really. It's completely dependent on Stokes law. So verify the validity. How? This was really surprising. So here one is pulling the air, the ball again, and obtain the diffusion coefficient in the unperturbed liquid. So pull it. So there are three ways we can check, as I show one by one. We set up a steady state. So we did this experiment. Set up the steady state. It took a long time actually. It took started when in the midway in writing my book, it was sometime last year. Or before that. The steady state velocity, then you know the force which you are supplying from outside. So another thing that we wanted to dependence on the interaction potential, and that nobody talks about, except Luanzik talked about it. Harrison and Luanzik when he tried to this pressure diffusion or noble gas diffusion in hydrocarbons and system scientific. That's just beautiful stuff. Okay. Stokes law must break down. Okay, you are going to pull it, you pull it very fast, you know, they are little linear response. But at what force? Does it? When we thought that we break down very fast. I really didn't have any faith of these hydrodynamic things. And how does it break down? And what else can we learn from such experiments? And here is system details. And there are a large number of system studies, 23,000. As I told you, more than a year, 2 systems, there are Jones and Dave. All are dimensional units. Interesting thing for you is to force. The last equation, please note that people you turn 4.87 into a star. F star is the number you see. So that's a piconewton. I don't have too much of it in terms of piconewton, but at least it is here. So the standard position. Now comes the surprise, and these next 2-3 transparencies are one of the main results. Initially, I told Shubhajit to take a little low density because I didn't want to create too much of a flow. I want to stay linear. That was a good choice. Temperature 0.8. Why? Because we want to deep in the state. Remember, critical temperature of liquid Jones is temperature density 0.32 and temperature 1.33. That's a critical point of the energy. So we are well in the liquid state. But look at that, it's beautiful. There are many beautiful things are here. And it is a Langevin dynamics solution. Why you had to do Langevin dynamics? The there is a little noise added to particles. Otherwise, they become unstable. And that was something I worried a lot about, but I'll show you that even with that, the results make huge sense. And so basically, we are relaxing the system a little bit with the small, very small Langevin noise. And why Shubhajit did it in the beginning? Because there are 2 other simulations people have done who have done exactly the same way. And they are very serious kind of work. That is one, but we worried a lot. We did a lot of English simulations also. Now, and then it is the soft sphere. In the soft sphere, the surprisingly here it breaks down at 5. Remember, they 4.8 turn into the Death Star. In the case of soft sphere, it is valid for such a long time. Beautiful linear regime. I'll show you why I believe these results are correct. And that I sent it to Scott Rice, the 90-year-old man. He gave me a wonderful comment. He also is saying it's very remarkable, but many things we still don't understand. He also raised the question of the noise. Okay, but without noise, we don't get, because the system don't relax. Probably one or two huge number of time, and we have a periodic boundary condition. I study the effect of that. Okay. So this beautiful straight line, and now change to different. Now, one important thing is that when you go to higher density, now the higher density means that you have a cage effect. You have a far more stronger interaction. So in both the two cases, by going to this, not greatly, but somewhat higher density, 0.7 to 0.85, temperature is important, but not that. So anybody knows in dense liquids is the density it plays the card. So it becomes very hugely reduced the limit of validity of the Stokes law. Now, what is the reason I believe that these results are sensible? So here are the table, which is calculated from Stokes law and from Einstein. How is Einstein calculated? You go to unperturbed liquid. In unperturbed liquid, you get the diffusion, nothing, no pulling, nothing, and you get the friction from zeta equal to kVt by d. And Stokes law by pulling and relation between force and the average difficulty. Look at that. Everywhere they are very, very close. There is, other than very close, there is no other systematic thing in that. So 7.0, 7.1, 5.96, 7.9, 7.8, 7.4, 6.4, 6.4. Then are Jones and Stokes here, 16, 16, 13.6, 13.5. Amazing. Here, so many state points and so many different cases. I've given you here six different cases everywhere. Stokes law is working wonderfully, and completely agreement with Einstein. This I did not expect at all, and so okay. Now we did the deep velocity of different size stack particle. Two is, there is no greatly systematic thing, but going to stack particle size twice the, for example, half or one, it agrees better. That is what we expect of this, because the difficulty of going over to larger size, so we tried up to size 3, then 3 is a very big size. D3 means the whole volume of that particle is kind of monster, like 3 cube. So it really pull it displays too much liquid, even in a 25,000 system particle. Maybe you want us to go to, like people do in Greg Watts screw, 150 million. I have to probably ask him to do this if I ever go there too. Though I don't think he'll be interested. But this is system size dependence. The whole thing holds. Okay. Both in Lennard-Jones, the linearity assumed by Stokes law for colloids hold at the atomic scale. And then diameter dependent friction, and it again the proportionality friction and size is completely different. Now there's something really very, very interesting that comes out. Since we know the proportionality and we know Stokes law, we know the friction, we can now go and further check Stokes Einstein. So we calculate the viscosity and we calculate the prefactor. Remember, it is phi pi. Here given here on the right hand side, Stokes Einstein relation as a function of zeta equal to C A. Eta A is the radius of the particle. We know C is 6 pi in Stokes, 4 pi in split boundary condition. And here I can get the C from these graphs for Lennard-Jones and soft spheres. And look at what we get. Lennard-Jones, which like smaller sticky, 5.6 pi, soft sphere is a little bit less sticky, C 5.35. It's just I'm saying this. You see, we did mode coupling theory calculation. We got results and all these things, but here one is systematically looking and finding the numbers and the trains. So this was the old paper. The reason I really didn't believe that this will work was this paper. Yes, we got when we did a very rigorous mode coupling theory calculation, very well cited paper. And we did get a 5.1 pi. He's an open hand, did series of work, and they always said it will be 5 pi. But look at the calculating the friction against viscosity. So it is a calculation, an implicit function. You change density, you change temperature, and you get viscosity. Everything theoretical, no computational solution here. You get the viscosity, and the other end you get the friction from mode coupling theory. That's fairly sophisticated because that includes current mode, binary coherence curve, density mode, everything. Very detailed calculation with a very accurate dynamic structure factor and self-consistent calculation. We were also very happy there that to see how flatness at large viscosity, where hydrodynamics sets in. That hydrodynamics breaks down at low viscosity is well known. Now, however, what we found that time is 5.1 pi, and that is almost in the same ballpark that we are finding here. Okay. So this is now relation between diffusion and friction and viscosity, and the Stokes-Einstein relation, Stokes law within our scheme of things, Stokes law working beautifully. In my book, pretty large friction, I'll give you what is that, what I mean by large and small, I define for you, and because that is very important. Now, so next, one more thing, and that again was we started doing it. Can you please mute? Okay. So system size dependence is the one that can give a lot of things. When we started doing that, we didn't know. We knew that Biman has done quite a bit of work on this, but I didn't know the papers. I once discussed with Biman that people are talking a lot about that paper, which is almost, hugely famous work. EA and Biman, I'll talk about it. They proposed a relation of the following form. And when I saw, he told me himself the result. I was very, very interested. I immediately told him, sometime I still can solve system like I did on the Amazon board almost instantaneously. So I derived from Karim, and he did not like it at all, because he has different interpretation, and I talk about the interpretation. Okay, so this is the form, very singular, very nice, very appealing form of the size. L is the size of the box, cubic box. The infinity when it's infinity, and 1 minus area. So now we already have done about 8 different sizes. Now first let me derive the thing that I derived. So velocity correlation function can be expressed in terms of two terms, essentially density term, which I'm not going to go, but the transverse term, because it is good to do this input. And this is the generic form, done long time ago by 1984 by Castellan. Finite system, however, I do not have this. Q is the wave number, Q is the Pattis function, CTTQ is the transverse current correlation function. You don't need to know too much of that, except that current you can define by some velocities, and then if we are transforming it to IQ dot, and then Q z axis that you define as the transverse correlation function, which is intimately connected to viscosity. And you can derive that from statistics correlation function. There is a spelling mistake, but that's okay. In finite systems, you do not have zero. You do not have zero wave number. There is a huge problem in critical phenomena. When they try to do critical phenomena, then they have to develop finite size scaling. So you have a 2 pi by L. So now I derive the 2 pi by L infinity, what I am measuring in the experiment. And I write that as 0 to infinity minus 2 pi by L. Now, asymptotic, first term is my asymptotic result. Second term is my what I am getting, L dependence. Now, I integrate the velocity correlation function, I get diffusion. Important thing in that, there is another integration over time is missing here on the right hand side. It is 0 to 2 pi by L and 0 to t. Now, look at 0 to t integration. That is bringing down 1 minus eta q square. Q square get cancelled. This is well known divergence synergy. You have now 0 to 2 pi L by dq. So now that is 2 pi by L, so that's 1 by L. So from transverse current, because of this singular form of the Q square and the current correlation function at low Q, e to the power minus eta Q square T is exact. So I get a 1 over L dependence. This I think is a beauty. Now, what does hydrodynamic does? Analysis based to be far more complex, but those who don't know the Moore coupling theory, they find Moore coupling theory more complex. Chemists don't like number dependent description. And when I was doing all these things, I found several problems with Casey Hines, and Casey roughly told me, Biman, I don't like your number stuff. So I could not say him that, of course, because you are wrong, but I could tell him that. I like him very much. So analysis based on interactions between point force. So you have a point force, 2 point forces interact with something called oscillatory tensor, right? One, if you generate a flow, is the same thing as the advective force term. Then Ye and Homer used a beautiful thing of Carpenter theory of interactions between polymer bits. That was translated into the interaction between point forces. And this was done by, this analysis presumably was done largely by Prof and Stokes credit to Luanzik for doing it, but never publishing it. But
if I may interrupt you once, will you please explain what you mean by point forces? I did not get that.
And a point force is the force that we are dragging a particle. Okay, so the point for a localized force. So you can do the calculation by point force because you want to think only of the distance. You don't want to have the diameter, then you have to take care of the extra correction term. So we assume in hydrodynamics as a that you are exerting a force at a given point. Okay, that's the standard area of oscillatory tensor. Yeah.
Okay, thank you.
So, and in our case, we are molecular length scale of say 25,000 particles. That's reasonably big. So my one tag particle, one Leonard Jones of sphere is can be considered as a point particle in scale. When you go to larger system, it becomes more point. So final expression is really and it is a very non-trivial exercise, but everything is oscillatory tensor. Everything is hydrodynamics and is the non-molecular. But mode coupling theory is everything is molecular. I can do density mode everything. But whatever it is, again the same form, and both have the interesting thing is both have 1 over eta here. In this my form, when I do the integration, there is a t. I told you 1 over eta comes in. So it's eta L. I've corrected now, but I think I'm afraid if I go out, I won't be able to come back on it in A. But 1 over eta L everywhere, 1 over eta L here also. And yes, completely they are fitted by found zeta 2.8. Okay, both approaches give 1 over L dependence, but quite different viewpoints. Now, what is this story? And this is another beautiful result that large number of systems 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see that 1 over L dependence is mind-boggling. 1 over L dependence works out. And I, without doing anything, said, okay, high density will be weaker. I expected crossover that because there is a density mode and viscosity is large. Remember, slope is 1 over viscosity. But that itself does not explain the whole thing. I'll tell you a little bit more of the numbers in a minute. One thing I say that would be that the soft sphere, 2 things I predicted. One is that as I increase the density, I have cage effect, local interactions, and local interactions will cut down the importance of the transverse hydrodynamic bond. That really happens. Second, I predicted that soft sphere, which has much less cage effect, will have a bigger difference at the 2 densities, and that indeed happens. Right hand side is this soft sphere, which you can see pretty large difference in slope. So this is again a new result where one is studying the effect of size dependence of the system. And I didn't like it, I must tell you, that such a strong size, even up to 23, because we reported diffusion, right? We don't do this exercise to do it, but we should do this exercise. It just makes our life difficult. But look at the beauty, look at the 1 over L dependence, and look at the the difference between Lennard-Jones and Stokes sphere. Again, we go and we have the Stokes sphere. You can see is somewhat larger slope, and which is A is the slope. D itself is not that greatly different, that we know. But look at the A. A is so much strongly dependent on interaction potential and also thermodynamic state of the system. Soft sphere, particularly last column, the huge slope that we saw, of course, in this case, the huge slope. Now, now I know the viscosities of two things well, which is 0.8, 0.7 in Lennard-Jones, that is 0.88, and I know I don't have a table, but at Soft sphere I know it is 0.72. So 0.88 and 0.72. So that is a kind of a 15%. But here my ratio is not 15%. It's much larger than that. And that means something more is going on. We have not yet evaluated the mode coupling theory. I did Ms. Sarika these days. That this should have been done in 2-3 days time. Okay. I should also say that not just Sarika, it's also because when I did these calculations, I had 25 years done. Okay, then I could do things in a day or two. Now, microanalysis solvent distance. One thing always bothered me, that what is the Stokes? My Navier-Stokes picture is correct or not? That is a very interesting question. So we did some microscopic analysis of the solvent response. And now I'll tell you what is big and small. One of the first things is that you do any analysis, you need a smallness parameter. How to get a smallness parameter? Okay, you are giving a force from outside, but the system itself has a lot of force, right? It's in thermodynamic interactions. So how do I get a measure of that? I'll get the mean square, root mean square force. What is the ratio between the force, external force, and root mean square? That is given in the two columns. Lennard-Jones is small 0.6. Soft sphere is valid for a much longer time. This is the value given at the breaking point, which is if external 5, F star external 5, and here it is 20. So 4 times, and that's trivial. But important thing is that these are less than 1. One could define, I think, like this kind of Reynolds number, that kind of a thing, a number here, which I intend to do, and then think in terms of that. First thing Navier-Stokes equation do, this is given in all the books, but I particularly recommend low Reynolds number Hydrodynamics by Nosgrave and the other book by Horace Lamb. They give you 1 over R dependence of the velocity decay of the away from the where you are creating the disturbance. We got somewhat faster than that, and but interesting thing is that the force is close, very equal to 0 where the particle is that I'm putting. Everything else is, nothing else is pulled. But if I pull, everything moves. That's what hydrodynamics also tells you. But what hydrodynamics tells you, that 1 over R dependence is not valid. And it's a fairly reasonable trend. Then you will see direction of cooling, and so essentially same picture. Now we know a beautiful paper which started many things in the 1970 PRL, no physical review by the other PRL also. Now that where Holder and Wainwright got the velocity profile, and it's beautiful. These guys moving, then the next one, of course, moving is stick boundary condition. They mostly also they get some momentum, and then ultimately it will go to 0. But after that it displaces liquid and create a velocity flow, and then it's kind of a vortex function. Ronzik told me personally that when he looked at that, he knew a hydrodynamics can be done, and that was the famous Ronzik diction paper which we used extensively. I should have given the quotation here. Okay, so allowing the radial distance for Lennard-Jones velocity. So let's go to density, because those are essentially. What I'm saying, they are kind of a pointless unless I do the hydrodynamic calculation and compare with hydrodynamics that we have not done, which is to be done. But this is something extremely important. Now I study the density in front, when I'm putting the Z direction, front on right hand side and left hand side. Now, if the liquid is incompressible, then density, velocity can change, of course, because there is a vector thing you're putting. Density should not incompressible. But here, no, there is a significant difference more in Lennard-Jones than in soft sphere. I have not checked, but I would guess, just like in viscosity, compressibilities are different. Lennard-Jones is soft sphere is less compressible because they are the same density. So this is a breakdown of the Stokes. We showed you several ones. One can go to beyond the first order perturbation theory. You have done something, but I think the analysis that you have done is not complete. So I'm not going to show about that. So summary is the present Kim's holds a molecular length scale with surprising accuracy. One has to be very, very unbiased and neutral, unemotional, whatever it is, impartial. I don't know what are the other terms. Soft sphere system continues to follow Stokes law until a much bigger. The value of computed friction is quite steep boundary condition. And that's been quite. Okay, I said I have to be partial. The validity of the presence is found to be lower at high density. Age effects become important. We performed a mode coupling analysis to understand the friction of that particle. So conclusion: despite the great importance, the range of validity of Stokes law remains shrouded in mystery. We suggest through the analysis of such aspects of interaction potentials independent, we can learn more. Good news is that Stokes law and Stokes-Einstein relations are obeyed. I think I should really talk with the hydrodynamics guys, which I have not done, because we have for a long time. I was not sure of the results. One of the reasons of talking about these results is that to get some. When you prepare a talk, give a talk, you think a little bit more than what you did. Okay. Thank you for your attention. Hello.
Sumon. Questions, please.
Yeah.
I'm here. Is there?
I'm here. Okay. Yeah. So thank you, Professor Bagchi, for a wonderful lecture. Now the floor is open for questions and discussions. I can see there is already a question in the chat box from Shobhik Sadhukhan. The question is, for the soft sphere, are these results in dilute limit or dense limit? What is the effect of increasing the density for the soft sphere case?
No, it is same density. So in a soft sphere, you don't have a liquid, right? But you have all the characteristics that of a liquid, in the sense that you have a radial distribution function, which is not too different from the Lennard-Jones. Lennard-Jones is a little bit more high peak, but otherwise, same kind of a ripple effect is there. So these in the points density 0.7, I'll say it's moderate density, and 0.85 I'll say high density. If it helps you to understand hard sphere, which is not too far from soft sphere, hard sphere freezes at density 0.936. Liquid density 0.936, packing fraction 0.49. So packing fraction 0.49 is pretty high because your maximum packing is 0.74, crystal close packing, and random close packing is 0.62, 0.64. Better take random systems of 0.62. So, and it goes to a solid packing fraction 0.54, and density 1.02, reduced density. So 0.85 is pretty much deep in liquid. 0.7 also is liquid. I won't say dense liquid, but I'll say moderately dense. That means you will find a coordination number around you, something of the order of 9 to 10. That many neighbors you have around you.
Okay. Is there any other question? Please feel free to raise your hand and then ask the question yourself.
Sir, I have a question.
Sure.
That is, if you are sitting at the liquid-like density and change the sphericity, so how, up to what limit should it continue the validity of the Stokes law? What do you think?
We are already setting up, hopefully. I discussed it with Shubham that we
Geber type potential something.
Yeah. We setting up and so because he did a lot of work with Poulet and Oblet recently, both in glass transition and in Boltzmann H theorem. And so the one thing that will happen, you start with say it's vertical position. You are pulling it. So first thing will happen, the force will be divided into rotation and translation.
Right.
So rotational translation coupling is very, very important. You also have worked on that, and many people have worked on that. I don't know. I cannot venture a prediction of the validity of Stokes' law because I don't understand the validity. And I told you, we're still, everybody does it. Small term, friction term. Like total friction is 10. We are adding Langevin, which is 0.5. So total friction, you get actually 10.5 and you take out 0.5. Now you say that why that is correct because random noise term is orthogonal to system dynamics. So when you take the averaging, that correlation is 0. That is the validity of Langevin noise. Everybody uses that. Now, the validity of Stokes' law is to me came as a surprise. Not just Stokes' law is linear and but friction is so close to almost identical that one we get in unperturbed liquid from Einstein. This itself I don't understand it. Now, secondly, what you are asking of late or correlate, it will be very interesting because when I can test Pairings equation.
Right.
And so remember in Pairings equation, translational friction depends on the aspect ratio.
Right.
But what is wrong about Pairings equation, it does not depend on rotational diffusion. If you do a mode coupling theory calculation, as we have done once, you would know translational friction is dependent on rotational relaxation and rotational diffusion depends on translation. Right. So they are coupled. But that is one greatness of mode coupling theory because that tells you very simply what to look at. And we are really guided by mode coupling to a great extent. I don't know. I would really like to see slightly oblate and slightly project.
Right.
Like 1.2 that we did in glass transition, 1.2 and 0.8 aspect issue. And see what happens. I think we will, if Shubham works, we will be able to give you result in about 2-3 weeks time. That's the scale he works. So long he's healthy and when he's not sick.
My feeling is that the better is the packing around the tagged particle, the higher probability is that the Stokes' law works.
No, I think it's the other way around.
Okay.
Because the following is that when and we already saw that exactly opposite to what you said, that when you increase the density, then the validity goes down. The reason is that at least Stokes' law, the way mode coupling theory people have derived, and I show the derivation here to you, that is this derivation. This derivation that depends on only on the current. Now, if you now add density mode has dq/q4, and if it is dq/q4, and you have a dynamic structure or small q, remember dynamic factor nothing but the relevant spectra. So it has e to the power minus aq squared. So I have dq/q squared. So I have a 1 over L cube dependence.
Right.
So that dependence is stronger. Actually, I very much expected it to see a crossover from density mode to when you increase the force from current mode to density mode. Large system size dependence, at least muted who is doing that. People are so insensitive sometimes. So 1 over L cube is the density mode.
Right.
So that's why when you have more cage effect, I think the Stokes law will break down. We have not been able to find that. And that's another puzzle. Why we are not able to find that? Probably more higher density, you have to go to lower temperature. Then see, the basic idea is that when you go to larger and larger viscosity, lower and lower temperature, then this e to the power minus eta q square t, that is CTT/QT, viscosity becomes large. That decays very fast. So transverse current mode, low, small wave number decays fast. But the dynamic structure factor, that is dependent small q on the thermal diffusivity, that has much weaker wave number thermodynamic state dependence. So density mode will not be affected that much by lowering temperature, but transverse current mode or increasing density, transverse current mode will be more. So it should hand over the dynamics to density. If that happens, then I would have gone over LP dependence. We have not found it.
Okay.
Another possibility is that diffusion, viscosity, these are still dominated by long time processes.
Right.
And that is one more thing that could possibly happening.
Okay, thank you so much.
Yeah, so Snehashish has a question. Snehashish, you may go ahead, please.
Am I audible, Sumanda?
Yes, please ask.
Okay, wonderful talk, Professor Bagchi. So, sir, I will definitely wait for your book. Hopefully, it will come by December, as you said. I will definitely purchase the book and read it. So, I had one question regarding this this Stokes-Einstein relation and its breakdown for not for simple liquid but for complex liquid. So here, because this Stokes-Einstein relation is based on many approximations we know, but so the general comments we normally get from different reviewers, then that for complex liquids, why you are looking for the validity of Stokes-Einstein relation where it already breaks down for simple liquid. So and that's why
it does not break down for simple liquids. That's I also expect it. It's wrong. It does not break down for small liquids.
Yeah, but if you see the quantitative relations, then it's difficult to match. Most of the time we do like
no. That's because Harrison paper, if you read, then that was the conclusion of this fractional viscosity dependence Pollack and Enyart. Pollack and Enyart, probably 1984, around that time. Then Harrison was 87, not 85. They're next week, almost 1 year or 2 years ago. Once he told that the Pollack and Enyart analysis is wrong because they made the viscosity fractional keeping the factor constant. Luanzik said is exactly opposite should be done because the Navier-Stokes equation, as I emphasized, is a linear viscosity. So there is no way hydrodynamic prediction will have diffusion, a fractional viscosity dependence. It will have 1/8, but the factor in front of it need to absorb the details of solute-solvent interaction. Yeah. Luanzik would have been very pleased to see that how Lennard-Jones and short sphere are different, and that's what he was. So what you tell breakdown of Stokes-Einstein is sometimes very silly. It is not the breakdown in the convention that the fractional viscosity dependence. Viscosity dependence might remain valid, but the prefactor has to be renormalized as they go from solvent to solvent.
Yeah. Okay.
Pollack and Enyart went to hydrocarbon and they changed, I think, propane, heptane, hexane, heptane, octane, like that. And so they have. So now consider a xenon interacting with a pentane and a xen or propane. Propane is not a liquid, that is, so let us with butane. Okay, it is interacting with a butane and it is interacting with the octane. Then the solute-solvent interaction. So the diameter that the liquid will see is different on its own scale. Like a very tall man perceives the height of the people differently, right? You know, this joke that there's a very short man went over to a big basketball player called him Abdul Jawad, 7 feet 7 inches. And the common joke was that you ask them, how is the weather up there? And so this shorty went and asked, hey Karim, how is the weather up there? Karim Abdul Jawad was drinking Coke. So he poured it on his head and said it's raining. So it is like that. You know, you scale. So the scale is changing. So solid-solid interaction scale is changing. Now think of that protosquare, but that was done by Herzberg. No, that very one famous paper, Benamot's Bondian Herzberg technique, that we used in one of our papers, Nilashish. And okay, then you find that he changed the interaction between this kind of, up to you went up to decane, dodecane. Interaction between two dodecane as a sphere, spherical interaction, and mapped and found van der Waals parameters and radius. So they change. So if you breakdown of Stokes Einstein should enter more through the diameter of the diffusing species.
Yeah. Okay. So if you think that fractional Stokes Einstein is okay, by different way you can tell that the Stokes Einstein is valid. So then it's fine. Yeah. Okay.
No. I'm not saying Stokes Einstein valid. Stokes Einstein always has two parts. One is the radius part and this viscosity part. I am saying it is not working. But
yeah.
In a simplistic, very simplistic way, if we plot against viscosity. No, when we are doing the chemical reaction dynamics, especially address this thing, Fleming introduced what is called isoviscous rate. So he took the viscosity out, and then only, what he did, he makes solvents such that he was measuring the rate as the same viscosity. And very read his earlier paper, or in my molecular relaxation liquids, I think I discussed isoviscous plots. Those became very famous. So you have to take such care, and it's a lot of work. For experimentation, it's okay, but for theoreticians, it's even more difficult because you have to do so many things and so many experiments and so many computer experiments to find the right. So what I'm saying, do not compare apple with orange.
Okay.
Whatever you do, have a kind of enlightened view of the problem, not the limited view.
Okay.
Okay.
Sir,
Yeah, please. Yeah, go ahead. Yeah.
Sir, although it might not be very relevant, this question, but as you said that this
I don't understand. I cannot see you. Because I have made it so small. I don't know how to.
It's Rajesh Da. Please.
Rajesh, your voice is changing. It's like mine also now. Go.
No.
Okay. So what I am saying is that you said that as you go to dense liquid, then Stokes Einstein relation even more valid. That's what your plot shows, right? If I understand it correctly.
No. You understand just the opposite. Right now, what you find, we go from high density to low density, Stokes sphere. Stokes Einstein continues to be valid with surprising regularity, and I did not expect that. And it's a very painstaking, very long simulations, and I don't think anything of this kind exists. It continues to valid with surprising regularity. What I'm saying, the discussion that Ronit and I was having, that at some point the friction should be more coupled to the density mode.
Okay.
That we did not see. And density mode has a different 1/L dependence, but there is one more thing that can be there. since it's 1 over L cube dependence, it has a much lower sensitivity to L. So we might have to go to even smaller particles like 120 systems and 128. But the problem is that if you go to 64 or so, then the whole thing might become unstable. So we are kind of bounded, and we are surprised, and but the signatures of compressibility breakdown is there. Velocity profile to be fitted a little bit more to hydrodynamics, and see how good, because this system one should be able to do that, and how good the velocity profile matching up to the various Stokes equation.
So how like it is, how then it can one like in for supercooled liquids, as you have also mentioned many times, right? And we know that it Stokes-Einstein relation breaks down severely as we go to supercooled liquid, deep supercooled liquid, right? So how like that is then like we can explain, obviously in terms of mode coupling theory, you have mentioned again and again.
I don't know whether it is breaking down as you are saying. See what is not working, that all of us know. The diffusion gets uncoupled from viscosity. Okay. So now Einstein, the logic goes like that: D equal to kVd by zeta. That is exact. So now we are going to use D equal to say 6 pi or 4 pi eta A. Then we find that diffusion is no longer coupled to viscosity, but that is nothing to do with we got a paper, we can send it to you. It has been submitted, Shubham's work, very long paper on the glass transition in orientation of liquids, that liquids with orientation. Most of the simulations did not consider, but after doing that, we found practice to CO did one. The basic idea when you go to supercooled liquid now, basic understanding, and this is been around now for about, I'd say about 20 years. And Sarika and I wrote a paper that was in 2000 that when you go, the liquid is heterogeneous, and the heterogeneity because once a density fluctuation is there, the density fluctuation decays very slowly. So your probe, say you have a multiple probe like market gas experiment, and you are going to see each probe in a different environment. Now each environment Stokes-Einstein probably working, but when you sum them up, they appear to be not working.
Okay.
So because diffusion is average over 1 over eta, and
right.
1 over eta is a average is over a distribution where eta is different, and diffusion on the other hand is scales to faster processes and viscosity scales to slower processes. So so that is the main reason of breakdown of Stokes-Einstein. Nothing, I think it has very little to do. Okay, apparent breakdown of Stokes-Einstein, but I do not think it has anything to do with the real breakdown of Stokes-Einstein.
Okay.
That I don't think doesn't happen, or happen much more than
Thank you, sir. Thank you very much. Thank you.
Acha, here I have one comment. This is discussing. Can I just tell?
Sure.
Okay, sir. So as you said that for supercooled liquids, there are different domains or different dynamical modes. If I consider different modes will
not different modes. I did not say different modes.
No, you said different part of the dynamics. You said
no. What is that? If you have heard it, it's called mosaic picture. And a mosaic picture means one is the thing more or less established, accepted now is by comes from many people, mainly spin glass, but exploited enormously by a random first order theory called arc by Peter Walling and Kirkpatrick Thirumalai. And that mosaic picture means you have divide the system into grids, and the grids, each grid is not small, pretty large, maybe few hundred particles. And then you are studying dynamics in each grid. So now you're probing in many different grids, and so each grid is seeing different dynamics. Dynamics is heterogeneous. There is a quantity called dynamic heterogeneity. It's extremely well known. It is almost like, first grade or second grade in glass science. And it is that much we have calculated. I think everybody in my group has calculated the dynamic heterogeneity. So Biman Jana did the first one in water. And Sikal Sassi told me that the first time water typhoon was calculated. But anyway, so you have to again and in one term I'm using that you have to take an enlightened view of the subject. That means what is enlightened view? Enlightened view is that I cannot talk about Rabindranath without reading at least say 20-30% of the writing. Enlightened view means you have to see the mosaic structure. That's the one that people believe now. And not only they are different. So it is like, consider the following. You have a large system, you have 1,000 liquid-like region and 10,000 solid-like region. Now, on top of that, the regions are changing to solid to liquid and liquid to solid. And there are further complexity because solid to liquid has a one rate and liquid to solid transition as one. So this transition is superimposed on the internal or inherent dynamics of the mosaic structure. Okay, that is the main reason of the translation rotation coupling, that or viscosity diffusion coupling. This is Marketing has a beautiful word which says during one, as I go super cool more and more, the exact verbatim quotation is that the molecule is translating more and more during one correlation time. That because correlation time becoming larger. That because correlation is married to slow domains. Translation is married to fast domains. I know it is too much for probably you guys, but these are the things we know for I'm saying about 20-30 years. One of my reasons of giving this talk, essentially Stokes for molecular length scale, is to tell people these things which have evolved.
So for this dynamic heterogeneity, if I say very dynamic heterogeneity means that diffusion coefficients at different portions have different diffusivity. Particles of different portions have different diffusivity. Some particles are very fast, some are very slow, depending on the regions.
Right.
Now, from that point, if we think that from your point that the fast particles which are moving very fast, they are also independently coupled to viscosity, and the slower particles, they are also coupled to viscosity. But when you are taking it as harm, then this breakdown and all this decoupling and all these things are coming. Right?
So you wrote a paper with Sarika. You please read that. That has
okay, I will go through
very well that the two different averaging. You go to stress time correlation function. Viscosity is integration of stress time correlation. Now, stress time correlation function integration will contribute more to, just 1 second, more to flow domain. I'll just come in a minute. Sorry. So stress correlation function integration which gives the viscosity will be more contribution from the slow domains. Okay. So, but however, if you do diffusion, then you are saying how much of particle is moving. Then that comes from fast domains. So they are completely different things. That's the reason for the recovery. And it is established now. This is more or less Bible, or no, Bible is not the right term, but pretty well known, pretty well accepted. I am really surprised that I still see many papers coming out, JCP, JPC, they don't seem to know. Even in complex liquid, you can extend it. In complex liquid, you have one more order parameter or one more thing, say orientation or arrangement. They are different in different boxes. And that is itself will explain again if you translate this to that logic. And so I think my book doesn't have too much discussion on this, but because the size is really clear, and I was trying to develop a course of time dividend step math, so I couldn't go detail into too much into that. Who are the people? Problem is that people don't write these things. People talk in conferences. That's why conferences are important. And talks are important, where you can probe and get the information. So yes, physical chemistry community needs little bit more enlightenment.
Is there any other question or comments? If not, let us thank Professor Bagchi once again for a very enlightening lecture, a very fundamental topic. And so that brings us to the end of today's seminar. And we'll, of course, the recording of this lecture will be uploaded on in our YouTube channel. And the previous lectures also by Professor Bagchi in the same series are also available there, particularly for the students. So please feel free to go back and listen to those lectures once again.
Suman,
Yeah.
next time I go, when I don't know when that will happen. Because I have not gone to Calcutta now, except that one small trip to Kolani. It was very nice, and I see I didn't even go to Bali. I have not been there for years. But if I go, then I think I want to listen to that once more and make some corrections.
Sure.
Because it's in the public domain now.
Yeah, sure.
Sure. Okay.
Okay, so yeah, and our next lecture in this series will be announced in due course of time. And if you are subscribed to our mailing list, of course, you'll receive the announcement. So till then, goodbye everybody, and thanks for attending this seminar. Okay.
Okay, bye.
All and bye. Yeah.
Bye.